This is webinar number 4, and it's on the topic of data cubes, which is a building block that we have included in JackDaw in the past few months. And this walkthrough will be a brief look at what they are. So what's the background, what's the structure, how do they work, and how can we put them to use in our various projects. And this will be a fairly technical talk, so some of you might regret your life choices over the next few minutes, but we shall see. I am Runar. I have been around for a disturbing amount of time, and I work for a Norwegian company called Avinet. I have been around for a while, and I've been doing quite a lot of projects, so my strengths are more in breadth than in depth. I have participated in many different things, so I know a little bit about many things, but I don't know everything about anything. So you will be able to rest me on many things. I am a Norwegian, but I'm exiled to Brussels, and I plan to return to my native land of Norway to die sometime. The structure of what we're going to talk to here is split into 5 simple components. So what are the data cubes? Why do they matter in the context of Polyrural Plus? Then we'll have one section that goes on how we can prepare data for data cubes. Then how can we put data cubes to use in your projects if and when that might be relevant. And then just a summary and closing for leaving on a high note. So the first step is the introduction. What are data cubes? So the first thing we have to see then is the problem. And the problem is trying to see connections. In the domain of GIS, where these data cubes have sort of, well, data analytics and GIS, where these data cubes have grown out of, it has always been the assumption that people want maps. Maps is always the only output. And then you create thematic maps and you do some magic analysis, and these analyses are big and manual and complicated. And eventually you end up with some sort of result. But the flexibility to sort of play with this and see what is the impact of different variables and so on becomes difficult, because it's some sort of a big manual process that has been put into effect. So seeing connections is the big thing of data cubes, being able to pinpoint locations that satisfy many different criteria in terms of location, in terms of time, in terms of specific properties. And that becomes very difficult when you are dealing with data that are scattered across a multitude of different sources like tables and maps and spreadsheets and God knows what. And also when we deal with the domain of rural development, oftentimes the information that you need is not even data. It is something that lives in the minds of people who are involved. Municipal engineers who've been around since the dawn of time and who has a sort of an internal database of anything that needs to be known. And then if we do actually have data, it's hard to combine them because they have different scales, different units, different timeframes, different all sort of things. So the purpose of the data cube is then to provide some sort of unified source of truth for decision makers. And the idea then of a data cube is that we should organize information in such a manner that we can pinpoint very easily any attribute at any point in time at any location. And then also to be able to correlate these so that we can put conditions for all of these spaces. And if we do that, we should be having some sort of a reliable source of truth that we can put forward and use in other analytical tools. So the basis of data cubes is gridded data. I have stolen an illustration because my own was not very beautiful, but I have stolen an illustration with a different spelling from what is considered conventional English. So parcels on top there is perhaps not the standard spelling, but nonetheless, the idea is, of course, that we possess information that sits in layers on top of each other or fused in the same actual space that describe some property of land. So there could be data derived from imagery like vegetation indices. There could be data derived from vector mapping projects like land cover. There could be socio-economic data like demography, and so on and so forth. And all of these, of course, vary over time, and they describe the conditions in a specific location. And then these may change over time. Terrain typically doesn't change a lot, can change a little bit once people decide to make a dramatic change to blow up a mountain or something. Parcels change quite a lot over time. Wetlands may change over time. Demographics certainly may change over time, and so on and so forth. So by putting these into sort of a multidimensional structure, where we in one dimension have the location, in the other dimension we have the time steps, and in the third dimension we have the property, the factual attribute layer, then we're able to describe so that for any given location and any given time point, we can set conditions for all the attributes that live in that spot. And we're able then to use that to do comprehensive raster calculations or analysis on a truly magnificent scale. So data cubes, they force on us, of course, and regrettably, some new standards that we need to relate to, the spatial temporal asset catalog, and the array encoding from a ZAR. These are formats that allow you to deploy data quite easily in the cloud, which is the rage nowadays and has been for the past 10 years. And they are fairly scalable in terms of handling very large scale. But done right, it means that we can answer in a heartbeat such a question as, show me all areas that are within 10 kilometers of a port, for an example, that had a market size of a certain size in 2023. And we could then vary that and slice it and dice it and find out how that changes over time. And we could use that to identify opportunities for locating something that is in need of maritime logistics. And this makes a departure from the conventional GIS, because it's not merely visualization, it's actually the possibility to do real-time analytics, where you are not relying on your eyes to identify patterns in thematic maps, but you're actually doing the actual analysis in real time. So why is this something that's useful for Polar Plus? Well, first of all, of course, we are working on rural challenges, and we need then some sort of a rural intelligence system to power decisions in this field. And cubes, they will not act as the only source for information or the only means of analytics, but they are one building block in this analytical layer that we try to do. And of course, they allow us to harmonize things in a way that allows us to query them, as I described in the previous slide. And the interesting thing is that they are particularly well suited to determine areas that are suitable for a specific purpose, or areas that have or are likely to have specific problems. And we can easily pinpoint these by adjusting the conditions for each of the dimensions in our cubes. And we will have an example later where I will show you how that works. The other benefit is that in Polar Plus, we are trying to use a sort of fusion between traditional spatial analytics, the GIS approach, and AI, as in large language models, to allow people to orchestrate and conduct spatial analysis using natural language descriptions instead of by the expedient of a GIS expert, a resident GIS expert, as has been the custom throughout the years in regional government and local organization. So once we want to do queries, spatial queries for any location with high resolution data and so on, this really doesn't go very fast if you're working on high resolution vector data. But if we slice and dice these data into or compose them into cubes and then slice and dice them, it's possible to do really, really big analysis with very low computing overhead so that we're able to serve very, very specific things. So in addition to being a sort of a good mechanism to see connections, it also enables us to run analytics at scale. And then, of course, since we are able to do analysis in real time, we are not sending someone off to an office to do some work on his own for several weeks and then come back with a magic result that was so costly to make that we have maximum the capacity to do 3 alternatives for anything we want to do. We have the alternative to do nothing. We have the alternative to do so much that we know that we can't afford it. And we have some alternative in the middle. That's the typical manual process of analytics now. But in this case, we are able to do analytics in real time, and we can show the feedback loop immediately to people who are participating. And that means that you can make small adjustments and see very easily the connections. And that is a good thing once we want to ensure buy-in from stakeholders in planning processes. So we are using it in Polyrural Plus for rural attractiveness indicators to identify areas that are useful or attractive for specific purposes, for innovation, for small scale agricultural business development, for energy production, for this, that, and the other. We can use it for determining accessibility and service planning, so dimensioning the number of schools that will be required depending on population development and so forth. We can use it to determine the market potential for establishment of new businesses, and we can use it to sort of monitor changes as things change over time. And then I thought I'd use a little example from an outtake from JackDaw, where I've asked to create a terrain cube for a small area. Now the dimensions could be anything, but in this case I have chosen to select terrain dimensions because it's a fairly easy example to understand and it's easy to see the correlation. So in this case, you see that the cube has 3 dimensions as elevation, aspect, and slope. And by adjusting each of them, you see that values that are completely within the blue interval, they are green. Values that are near the edges, they become orange, yellow, red. And areas that are entirely unsuitable fall outside entirely. So by adjusting these now, I can find all areas that are below 150 meters of elevation that face broadly south and that has a slope of less than, say, 11 degrees. And that tells me areas that are flat and that have a fortuitous exposure for my use case. I would like to build wind. No, I don't want to like build. Nobody in Norway wants to build wind because you get death threats if you build wind parks in Norway. I want to build a solar farm, and the solar farm needs to be in a relatively flat area. It should be somewhere with a fortuitous climate. And strangely enough, even though Norway is a country of horrible climate, we are on the Atlantic. The Atlantic keeps the winters mild, and so close to the fjord at a lower elevation, it will be quite okay. So I'm looking for areas that are below 100. I'm looking for areas that are facing broadly south, and I'm looking for areas that have a slope so that it is suitable for exposure to the south. And like that, just by dragging and dropping in the interface, we are able to modify this. And of course, you could replace these cubes dimensions with anything you like. It doesn't need to be elevation. It could be distances to markets. It could be distances to airports, and it could be number of hotels. And if you can find a place that has a low distance to an airport, that has a huge market, that has a very low number of hotels, okay, that could be indicative that there is an undersupply of that specific service type. And for someone who is trying to attract investment, trying to determine what an area can be used for, that's a useful type of information. Okay. To prepare data for a data cube, fairly easy. We need to have spatial data, and they need to be gridded. We don't need temporal data. In the case of terrain, for example, it changes very little. So, okay, it can be a point in time, but we should have, if we plan to combine data together into a cube, we need to have a temporal scale that is compatible. So yearly, monthly, or event-based data. And we should have whatever the topic we wish to observe. So in my case, that population, accessibility, slope, aspect, elevation, etc. We should harmonize these inputs because we need to make sure that, like this illustration I showed initially with all these layers lying on top of each other, that things are aligned perfectly and are not sort of skewed or offset. And for that purpose, we need to resample data to make sure that they conform to the same grid. And we should also use some sort of a naming convention so that it's easy to refer to these variables and understand which ones are what. So when we want to combine it into analysis, and then we should also consider that we had a previous webinar, number 2, I think, that was looking at a tool to generate centrality measures. And in that webinar, we presented a tool that is capable of doing all these things. So it's relevant to look to that. Now, having created sort of these grids, then we need to try and write the data cubes to some widely recognized and reusable format. So for that purpose, we have something called Stack with some data cube extensions. And they provide us with metadata, and they provide us with enough information that we are able to know how we can use a data cube. That, regrettably, however, introduces the need in our lives to know what Stack is. So that is sort of an emerging, or maybe it is a little bit archaic to say that it's emerging, but it is a modern asset catalog for spatiotemporal data. And it allows us, it's particularly well suited to describe these sort of large collections of imagery and rasters, data cubes and point clouds that have come in the era of big data. And it's sort of a successor to the more comprehensive ISO 1939 metadata standards that describe every data set with 248 different variables, including fax number for data owners, cousins, brothers, neighbor. So it's sort of a no nonsense to the point metadata standard. And it also transports data as JSON instead of these huge XML documents. So from our point of view, with data stored in a way that we can sort of easily retrieve it, a little bit on the same line as these tile caches that you find in web map applications. And we have metadata that transports and travels over JSON. It means that we have a very simple tool to access and slice and dice data from remote sources. So GeoJSON plus time plus assets plus catalogs. That would be Stack. Inside this Stack format, we have different ways to represent the data, because the data of a cube obviously has to be a large set of numbers. And the more dimensions, the more numbers, and they have to be chunked and sliced and diced in a way that makes it easy to retrieve them. So there are many formats for this. ZAR, Net, CDF, and Parquet is some of the most popular ones. We have standardize on using ZAR in Polyrural Plus. And this sort of creates a folder structure that lays out the document by its dimensions and provides a metadata file for discovery. And this is easy to deploy to any sort of storage. You don't need a server, really. It's all HTTP. So you can put this in any sort of storage engine that you have, both local or cloud. I put this in gray here for the sake that in our case, we mostly use our own infrastructure. So what is ZAR then? It's a cloud native format for chunked and compressed multidimensional data arrays. And it can take as many dimensions as you want and split them up into small chunks that makes it easy to retrieve data for many different locations, many different times, without having to iterate the whole big data file. All of it's independently compressed and becomes highly condensed and easy. It uses mainstream libraries under the hood, mainstream Python libraries, I should say, for creation. There's a rich ecosystem for that, but also exists libraries to work with this in JavaScript, C, Julia, Rust, whatever. And for us, I mean, the problem for us would be that if we were to sit on enormous single file data sets and we wanted to create a data cube at query time for some topic, we would have to open and read and consume enormous amounts of memory. Whereas in this mechanism, it's already chunked into small pieces that makes it easy for us to take the area we're interested in, the time period we're interested in, and the properties we're interested in without loading all the other overhead. And the tooling to create this, okay, GDL OGR, as always, a very useful library to deal with the spatial data, resampling, all this sort of stuff. Python, if Python is your language of choice, many libraries that are relevant. And once again, a sort of a throwback to this centrality tool that we have in Polyrural Plus that can be used for the same thing. Okay, data cubes in your projects. We don't know if you have a use for data cubes. This webinar series is oriented around informing external parties, both those who have participated in our Cascade funding calls and third parties who are interested, to see what sort of things is it that we build in our project. And so we are openly asking this question. Some people have written in Cascade funding project proposals that they are interested in using the technology ABC. And so for them, this acts as an introduction to what that technology is. For others, it might be just a concept or an inspiration or an example of something should be avoided to be done at all costs, depending on how you perceive it and how it fits your use cases. But let's say, what sort of applications could you envisage? We have a market potential app for rural entrepreneurs or planners. I mean, entrepreneurship is the domain of the private sector. The public sector generally should look at economy and land use. So we can sort of say this area is designated for commerce, this is designated for residential, this is designated for industry. What exact industry, what exact commerce? Yeah, okay. So there is certainly a vested interest in attracting certain sectors that are economically and labor market beneficial. But in general, there would be a dimension for the entrepreneur, there would be a dimension for the public planner. Determining accessibility in terms of defining both accessibility as spatial accessibility, but also accessibility as in whether we are underserved or overserved by certain services. Monitoring tools to see how things change over time and demography. What does demographic decline mean in terms of future service development, etc., and so on and so forth. For those of you who do partake in Cascade funding, there are some small expectations that we have of you, which have been, of course, duly described in the call. But it is an objective to follow standards as far as possible, open standards. It is an objective to make methods that are reproducible. That is not to say that you have to make your code or your solutions open source, but it should be documented in such a way that the lesson learned from what you do has applicability in the community. And finally, then ensuring openness. Once again, there is no demand that everyone must produce. I mean, if you make it criminal to have private data, then where is the business model? There has to be something. But ensuring openness where licensing and where the purpose allows. And then, of course, we would say that using the cubes, of course, makes it possible to remove some pre-processing work, and we will have cubes for about I mean, you can compose cubes from about 40 different themes, attributes that exists in our dataset today. So if any of those are of use to you, you are able to take them as input and use them in your own processes. And that would allow you, of course, to save some time on data integration, data collection. And it's also reusable across regions, of course, which means that this innovation has a scalability to it that you wouldn't have if you made something that is exclusively sitting on a custom local data model with custom local data. So then we are very much nearing the end. Key message that you should take away with you from this webinar: data cubes simplify, make it possible to query thing, as in thematic dimension, space and time for anything in a single structure at a very high performance. It's potentially a useful building block for a future rural intelligence system where you are trying to support actors in rural communities. It does have immediate value if you look at it on top of day-to-day tasks in GIS, and immediate value also in terms of scaling our capability for large-scale analytics in GeoAI, and big scale, mind-boggling scale. To those who might be watching this, call to action. Partners in the project should contribute or suggest datasets for harmonization. That is also the case for Cascade funding winners. If you have datasets that you believe would have a broad applicability, you must feel free to come forth and suggest those, and maybe the project can put them into these to our sort of database for you, and your cubes will be able to do more. For developers, we would encourage you to explore the cubes. We have some APIs and endpoints for that, and the concepts that we described here. And then you can critique them, or you can reject them, or you can approve them, you can use them, or you can suggest how we can make them better if you think that they are not good, but that they have the right of life. And then for people who are neither partners nor developers, but who are innovators, people who have some challenge of professional nature, who believes that the data cubes could have a sort of an applicability as one of the building blocks to solve those problems, we also encourage you to think of this puzzle piece. I'm using a lot of prize-winning metaphors here, puzzle pieces and building blocks and whatnot. The essence is there, though. And as I say, please provide feedback and suggestions to our approach. And with that, I just say one more thing, and that is that we did not invent data cubes. There are people close to us here who have done so. Peter Baumann is not terribly far away. There are people in the OGC community that are not far away. There are people in the EU research projects that have contributed to this. There are quite a few people that should be considered. So just for the sake of disambiguating, we are not claiming credit for having invented it. We have just adopted it and made it possible to generate data cubes dynamically for any area of your interest through natural language in JackDaw. So that would be the main thing. And with that, I thank you for your attention, if of course you paid any attention. And with that, I think the recording part of this seminar is more or less over. And I will just leave us on the starting screen and open for any questions if there should be any. And I have on the previous two occasions, I have a challenge that I talk a lot, and I have a deep anxiety for silence. So when I ask people to say something, I generally start talking before they have the chance to say anything because I become very uncomfortable from the silence. So in the last 2 or 3 webinars, I have said that I will now count 10 seconds in silence, uncomfortable silence. And during those seconds, if nobody seizes the word, I will consider the thing as over. So starting now, 10 seconds of silence, unless anyone wants to say anything. Okay, very good. With that, then I apologize for any sort of long-lasting damage I may have made to your mental health, and I wish you the best of continued days and talk to you soon.
Thank you very much, Gunnar. Thank you.
Thank you,
Thank you.
Huna.